Hello everyone. Today me and Ali we will be presenting our case study about the details of Atlantic Southeast Airline Flight 2311. On April 5, 1991, a target event unfolded as Atlantic Southeast Airline Flight 2311 operated with Empire Brasilia crashed near Prince Georgia. We will discuss the in-accident details, the investigation finding, and the subsequent enhancement in aviation safety that followed. Here's the flight details. Flight 2311 began its journey from Atlanta, Georgia, the city major airports, serving as hub for countless domestic and international flights. Was the starting point of our flight. The shuttle route was routing commuter flight, a path flown by many aircraft day in and day out, heading toward Brunswick, Georgia. The flight carried 20 passengers and 3 crew members. The flight meets its target and near Brunswick, Georgia, a devastating moment that would prompt a thorough investigation. The original aircraft assigned to this flight encountered some mechanical issue, so they had to bring in a replacement, which was an Empire Brasilia. This switch is a common practice in aviation to maintain schedule integrity when faced with unforeseen circumstances. The flight departure Atlanta at 13:47 p.m. Eastern Standard Time. Among the 23 souls on board were former U.S. Senator John Howard and NASA astronaut mainly Linear Carter Jr. Moving on, let's talk about the pilot experience. First up, we have the captain with a total of 11,724 flight hours, 5,720 of which were specifically on the Empire Brasilia 120 aircraft, which means that the captain wasn't just experienced, he was deeply familiar with all the details of the Empire Brasilia. His involvement wasn't limited to just flying, he played an active role in integrating the Empire Brasilia 120 into U.S. service. The level of engagement and knowledge signifies more than just experience, it's also shown a communicate to aviation and safety. His proficiency was recognized during his training, knowledge of the aircraft and systems, as well as excellent pilot techniques. Then we have the first officer, uh, who also brought a wealth of experience to the cockpit with a total of 3,925 flight hours. 2,795 of those hours were on the Empire Brasilia, highlighting a strong proficiency with this specific aircraft type, starting his flight training with Atlantic Southeast Airlines in July of 1988. He's quickly demonstrated his ability, passing his entire proficiency check-in in the same month. Both crew member extensive experience with Empire Brasilia. And now for the weather condition. On the day of the accident, the weather report from Prince noted a ceiling of 2,500 feet, scattered clouds with a moderate rain having occurred earlier in the day. The visibility was reported at 7 miles, which is generally considered a good visibility for flight operations. The wind was coming from 160 degree at 10 knots. These wind conditions are within a normal operating range and wouldn't typically pose a challenge to experienced flight crew, especially an aircraft like Empire Brazil. The temperature at the time was 78 Fahrenheit with a dew point of 69 Fahrenheit. The index as a warm and somewhat humid environment, but again, nothing would be considered a hazard or unusual for a flight operation. It's important to understand that while weather can greatly impact flight safety in the practical instance, the condition were within a manageable parameters. The moderate weather conditions highlight the external factors like weather were not contributing cause to the accident of a flight 2311. This directs our investigation toward other uh, potential factors such as a mechanical issue or system problem, which we will explore in the future details in the upcoming slides. Moving on to the accident. As a flight 2311 approached Brunswick, it was executing a standard lift downwind leg to runway 07. Everything appeared normally with aircraft and routing configuration for a landing. A gear down, a flap set on a stable descent path. Then, without warning, the situation took a disaster turn. Witnesses near the airport observed that the aircraft suddenly pitched upward about 5 degrees. This was immediately followed by a server lift roll, with the aircraft wing become almost vertical to the horizon. Such a dramatic shift from a normal flight to uncontrollable stats suggests a rapid and overwhelming issue, leaving a little to no time for corrective action. This uncommanded roll made the aircraft enter steep noise, first dive toward the ground. The witnesses, include some with aviation experience, noted the absence of visible fire or smoke before the impact, which rules out common cause like in-flight fire. The descent was not only rapid but also devoid of any signs that may typically precede an aircraft crash, such as engine noise or visible damage to the aircraft. The propeller was observed to be routing, which suggests that the engine were operational until the aspect is practical puzzling and point toward um, disaster failure.
Now, after getting a better idea at how the accident might have looked like from the crash animation, uh, we can now move on to the impact and wreckage. So the crash site was located approximately 1.5 miles from the threshold of runway 07 in a densely wooded area near Brunswick. This location, away from the runway and in a challenging terrain, added complexities to the immediate response efforts and subsequent investigation. For the wreckage path, the witnesses and first responders described a wreckage path that spanned about 250 feet. This path, marked by the damaged and downed trees, painted a very clear picture of the aircraft's final descent, which was steep and nearly vertical. The orientation and distribution of the debris provide critical clues about the aircraft's attitude and energy upon impact, which are key factors in understanding the dynamics of the crash. One of the most harrowing aspects of the site was the extent of the destruction. The post-crash fire led to a significant devastation. Much of the fuselage was consumed by the fire, with only the tail section remaining relatively intact. This level of destruction made the accident unsurvivable. The complicated the task of investigators in piecing together the sequence of events leading up to the impact. When they arrived at the crash site, investigators from the National Transportation Safety Board, or NTSB, went on a detailed examination of the wreckage. So, initial on-site inspections were important for ruling out potential causes like weather conditions, pilot error, or external factors. And as a result, narrowing down the focus to the aircraft's mechanical and structural integrity, particularly the engine and propeller systems. One of the most critical aspects of this of the investigation was the series of flight simulator tests. These simulations were designed to replicate the flight conditions of Flight 2311, allowing investigators to eliminate various potential in-flight failures. The turning point in the investigation came with the identification of a malfunction in the left engine's propeller control unit, or PCU. This malfunction allowed the propeller blade angles to move below the flight's idle position, a scenario that had not been adequately accounted for in the PCU's design and certification. The failure of this critical component was directly linked to the aircraft's loss of control and subsequent crash. Further inspection revealed contributing factors that worsened the situation, including deficiencies in the PCU's design by Hamilton Standard, which is the component manufacturer, and the oversight and the approval of this design by the FAA, or Federal Aviation Administration. This oversight in evaluating the failure mode that occurred during Flight 2311's final flight was a significant factor in the accident.
Investigators begin the painstaking task of sorting through the wreckage of Flight 2311. They're searching for any evidence that might hint at why the Embraer 120 rolled sharply to the left and crashed, killing everyone on board. Deep inside the propeller unit, investigators uncover an important clue.
Aha! There you are. We have a witness mark. Take a look.
There's a small mark where two parts of the propeller mechanism slammed together on impact. The witness mark might be enough to tell investigators how the propellers were operating. The marks tell Ritter the exact angle of the blades when the plane slammed into the ground.
These guys had a big problem with their left propeller. The blades were almost flat.
The left side propeller blades are at a dangerously low angle, one that is never used during flight. At 3 degrees, the blades are so flat they would act like a wall, blocking the flow of air the plane needs to maintain lift. Investigators study the mechanism used to control the left propeller.
Will you look at this?
They make a disturbing discovery.
It's completely worn down.
The teeth on a key piece of the gear mechanism, known as the quill, are almost entirely worn away. Investigators may finally have the lead they've been looking for.
This is what it's supposed to look like.
With its teeth worn away, the quill can't lock onto the gear system that controls the angle of the propeller blades. The discovery might explain why the propeller blades slipped to such a dangerously low angle.
Once we noticed that the quill teeth were severely worn, we started theorizing what would happen in that type of situation. And it was pretty clear that control of the propeller blade angles could be lost.
Ritter is certain he's found the critical clue: worn down teeth on the quill that could have allowed the propeller blades to slip to a dangerous angle. But he soon learns there's a big problem with his theory. The manufacturer says it's impossible. Engineers at Hamilton Standard included a fail-safe feature when they designed the propeller. It should be impossible for the blades to go flat during flight. If there's ever a problem with the mechanism controlling the angle, the blades are designed to move on their own to what's called the feathered position. A feathered propeller can't endanger the safety of the flight.
This has got to be it. This has to be connected somehow.
But Ritter isn't convinced by the manufacturer's assurances. His gut tells him the worn quill did allow the propeller blades to move to a dangerous angle. But without flight data, his investigation has hit a wall. He has no way to prove the quill brought down Flight 2311.
What's going on? You see anything? There's nothing.
So moving on to the detailed examination of the PCU malfunction. The PCU, a critical component, which is a critical component in controlling the propeller blade's pitch, came under intense inspection like what we saw in the previous video. Investigators discovered significant wear in the internal splines of the PCU's quill. This wear was not just a sign of aging, it was an indication of a systemic issue that allowed the propeller blades on the left engine to shift to angles below what is known as the flight idle position. In other words, the propeller blades were moving in ways they were never supposed to, which created aerodynamic conditions that the pilots could not overcome. This uncommanded movement of the propeller blades was pivotal. It resulted in a loss of control characterized by the aircraft's sudden and severe roll to the left. The situation was similar to trying to steer a car when one of the wheels just starts moving in an unexpected direction. No matter the skill of the driver, or in this case the pilot, regaining control becomes nearly impossible. And the investigative team findings were supported by a thorough analysis of the PCU's component. The worn quill, coupled with the discrepancy between the positions of the PCU ball screw and the pitch lock Acme screw, painted a clear picture of the failure. This disconnect indicated that despite the PCU's commands to adjust the propeller blades to slow down the propeller speed, the actual blade angle remained dangerously low. So the initial design and testing phase of the PCU, which was conducted by Hamilton Standard, revealed significant oversights. The testing failed to accurately simulate the in-flight loads and vibrations that the PCU would experience under actual operating conditions. Moreover, the choice of materials and finishes, particularly the transition to a rough titanium nitrided surface for the internal splines, deviated from the originally certified design without a full appreciation of the potential consequences. This change was not just cosmetic, it altered the component's wear characteristics and ultimately affecting its performance and reliability. As the investigation continued, it became evident that the design and testing decisions had not been adequately planned during the certification process by the FAA. The certification of the modified PCU design was based on Hamilton Standard's previous experiences and test reports, which in hindsight were insufficient to uncover the potential for the type malfunction that occurred on Flight 2311. This gap in the certification process highlights a crucial area for improvement in ensuring that design changes are thoroughly evaluated for their impact on safety, no matter how minor they might seem. The post-accident realization about these flaws was prompted a re-evaluation of the design and certification standards. It showed the critical need for comprehensive testing that closely mimics real-world conditions and for a certification process that rigorously assesses the safety implications of the design changes. Moving on, the Hamilton standard recognized the critical role that the propeller control unit or PCU malfunction played in the accident, and they took immediate steps to address the issue. The company issued alert service bulletins, which served as an urgent call to action for operators to inspect their PCUs for signs of the same dangerous wear found in Flight 2311 investigation. This was a crucial first step in mitigating the risk of similar incidents occurring in the future. The Federal Aviation Administration, or the FAA, as the regulatory body overseeing aviation, they also sprang into action. In response to the investigation's findings, the FAA issued a series of Emergency Airworthiness Directives, or ADs. These directives mandated periodic inspections of the PCU ball screw quills, particularly those with the titanium nitrided transfer tube implicated in the malfunction. The ADs represented a decisive regulatory intervention aimed at ensuring the safety of the flying public. And moreover, the FAA and the Hamilton Standard initiated a comprehensive transfer tube replacement program. This program sought to replace the problematic titanium nitrided tubes with ones that met the original safer specifications. And the success of this program led to the eventual termination of the AD status on the PCU, which signifies that the immediate risk had been adequately addressed. Okay, so moving on to the lessons learned from this accident. The first and perhaps the most crucial lesson is the importance of design validation. The PCU malfunction that led to the crash of Flight 2311 highlights the critical need for thorough validation of aircraft components. It stresses the fact that every element of an aircraft, no matter how small, uh, it must be carefully tested and validated under conditions that closely simulate actual flight conditions and scenarios. This can ensure that potential failures are identified and mitigated before they can lead to dangerous and catastrophic outcomes. Another significant lesson is the necessity for comprehensive testing. The accident revealed that testing processes and simulations must encompass the full range of operational conditions and potential failure modes. So this comprehensive approach to testing can uncover hidden vulnerabilities, allowing for corrective measures to be implemented proactively. Furthermore, the response to the crash of Flight 2311 reinforced the value of adaptive maintenance protocols. The aviation industry learned that maintenance practices must be dynamic and responsive to emerging safety data. The implementation of new inspection protocols and response to the findings from the crash investigation demonstrates how adaptive maintenance can effectively mitigate risks. So, in conclusion, the lessons learned from this tragedy of Atlantic Southeast Airlines Flight 2311 have led to enhanced safety measures and a continuous evolution of aviation standards, which ensures that the legacy of those lost is not in vain. It is through understanding and addressing the failures of the past that we can build a safer future for air travel.